Precision Aquaculture, Module 7, presented by Dr. Madisani Rukayat, PhD. Learning Objectives. In this module, learners will be able to define precision aquaculture and explain its role in modern fish farming, analyze the importance of data-driven approaches, explore precision techniques in aquaculture, evaluate economic and environmental benefits, learn modern techniques for disease prevention and management, develop competencies for implementing precision practices, promote sustainability and resource conservation, understand global trends and challenges in precision aquaculture. Introduction to Aquaculture. Aquaculture is the production of aquatic organisms under controlled conditions. These systems involve the cultivation of fish, mollusks, crustaceans, ornamental fish, and aquatic plants. This system also optimized breeding, feeding, and growth conditions. This sector plays an essential role in providing a sustainable food source, meeting the increasing global demand for protein. Basics of fish farming and aquatic systems. The need to understand the basics of fish farming is highly essential, in terms of knowledge about the species type, management practice, important components for a successful aquaculture operation. Water quality management. This is a continuous cycle of monitoring, assessing, maintaining, and improving water quality in different environments. Maintaining suitable water conditions includes the temperature, pH, oxygen levels, ammonia, nitrate, and nitrite concentrations. Aquaculture systems require constant monitoring and management to ensure water remains clean, optimal nutrient, and prevent stress or disease in fish populations. Nutrition and feeding. Most farmed fish are fed a diet specifically formulated to meet their nutritional needs at different growth stages. Proteins, lipids, carbohydrates, vitamins, and minerals are the nutritional groups required by the aquaculture species. Feed efficiency helps reduce waste and costs, enhancing sustainability. Innovations in alternative feed sources, such as plant-based and insect-based proteins. Disease management includes antibiotics therapy, vaccination, pond management, cultural practice, prevention by bioagents, chemical control, biosecurity methods. The most sustainable ways to control fish disease in aquaculture enterprises is by vaccinating them against bacterial and viral diseases. Breeding and stock selection. Genetically improve fish species for economically important traits, such as growth rate, disease resistance, feed conversion efficiency, and reproductive fitness. This system improves the breeding value of the population by selecting and mating only the best fish. Hatcheries play a crucial role in producing and distributing young fish to fish farms. Harvesting and processing. This is completion phase of breeding cycle, feeding, and growing aquatic animals to full growth, reaching market size. Harvesting practices vary depending on the type of fish and production system, but generally involve careful handling to maintain fish quality and reduce stress. After harvesting, fish are processed for sale, including sorting, cleaning, packaging, and sometimes filleting or freezing. Good post-harvest practices are essentially important to maintain product quality and to ensure safety for consumers. Types of aquatic farming systems. Pond culture. This system involves raising aquatic species such as fish, shrimp, prawns, and shellfish in ponds. Pond aquaculture can be done in freshwater, brackish water, or saltwater ponds. There are two basic types of pond culture. These are extensive and intensive pond systems. The extensive systems rely on natural food production in the pond to feed the fish. The intensive systems provide supplemental feed to the fish, which allows for higher production levels. Recirculating aquaculture systems, RAS. These systems provide a constant and controlled environment for the fish, allowing for optimal and fully manageable production. The system is structured from the outlet of the fish tanks where the water flows, through the mechanical filter, moves to the biological filter, aerated and stripped of carbon dioxide, and finally back to the fish tanks. This system allows intensive fish farming in areas with limited water resources. Cage and pen culture. Cage culture involves raising fish in cages or pens placed in natural water bodies. This system consists of a net suspended in the water column with a flotation system around its perimeter. Fish are confined within the cage for short or long duration, allowing water to flow freely and carrying away waste. Flow-through systems. This is an intensive feeding based on complete pelleted food that should be given to the fish regularly and in proper doses. Water flows continuously through fish tanks, bringing fresh, oxygen-rich water and flushing out waste. This system is commonly used in areas with abundant water sources, such as streams or rivers. This system, otherwise known as raceway, usually consists of rectangular basins or canals constructed of concrete and equipped with an inlet and outlet. Flow-through production systems can be predictive and well-managed than ponds. Aquaponics. Food production system that interconnect aquaculture with hydroponics, whereby the nutrient-rich aquaculture water is fed to hydroponically grown plants. This unique form a closed loop with the ability to reuse water and nutrients to support plant growth. Aquaponics is especially popular for small-scale urban farming, producing both fish and vegetables in the same setup. Importance of aquaculture in global food security and nutrition. Provide food that is fresh and locally monitored to improved food sustainability. Economic growth and employment. It provides excellent opportunities for employment and income generation. Environmental conservation. Decreases the need to catch more wild fish to fulfill rising demand for fish, helping to preserve fish supplies. Remote sensing for water. Quality monitoring, transformation tool in water quality monitoring, enabling real-time, large-scale, and non-invasive observation of aquatic ecosystems. Provides cost-effective, large-scale water quality monitoring with high temporal coverage and reasonable accuracy. Monitor important water quality metrics. Make informed decisions for sustainable water management, promoting ecosystem health and water security. Applications of remote sensing for water quality. 1. Aquaculture and fisheries management. 2. Climate change impact studies. 3. Monitoring and source tracking. 4. Eutrophication and algal bloom detection. AI for feed management and disease detection in aquaculture. In aquaculture, artificial intelligence, AI, makes it easier to analyze data from cameras and sensors to track fish behavior, identify symptoms of illness or stress. Use automated sensors to measure fish weight and length and adjust feeding schedules. This is crucial for the productivity, sustainability, and profitability of fish farms. Enables aquaculture farmers to maintain healthier fish stocks, reduce environmental impact, and meet the global demand for seafood. Integrated aquaculture systems with agriculture. Integrated aquaculture is the sequential linkage between two or more farm activities, of which at least one is aquaculture. It is the connection between different types of species cultured to utilizing the same water source. Integrated aquaculture systems that combine fish farming with traditional agriculture are an innovative approach to sustainable farming. Types of integrated aquaculture systems. Aquaponics. This system combines aquaculture and hydroponics in a closed-loop system. Fish and plants are grown together, and the nutrient-rich water resulting from fish waste is used as fertilizer for the plants instead of leaving the system. Rice fish farming. Integrating rice agriculture with aquaculture, most commonly with freshwater fish. It effectively utilizes land and water resources and promises to be a viable alternative to rice monoculture. Agro-fishery systems. This is a cultivation of crops through soils and other medium growing of trees, raising of livestock, poultry, or fish. Agro-fishery systems integrate pond or lake fish farming with nearby fields or crop plots. Nutrient-rich water from the ponds is used to irrigate and fertilize the crops. Sustainable aquaculture practices. Sustainable aquaculture practices refer to methods of fish farming that prioritize resource efficiency, ecological balance, and economic viability. This system utilizes land effectively for the aquaculture sector. Sustainable aquaculture places a strong emphasis on conserving resources, eliminating pollution, and protecting the well-being of fish raised for food, as well as the ecosystems around them. The development of sustainable aquaculture is also being aided by emerging technology, such as artificial intelligence for fish health monitoring. Resource conservation in aquaculture focuses on minimizing the use of natural resources such as water, energy, and feed, while maximizing efficiency and productivity. Conservation in aquaculture directly supports the recovery goals of native species and sustainable use of natural resources. As global demand for seafood rises, aquaculture has become a vital component of food production. Conserving resources not only helps reduce the environmental footprint of aquaculture, but also ensures the industrial long-term viability. Areas of resource conservation in aquaculture: feed optimization, energy efficiency, waste management, water conservation, space utilization. Environmental impacts of aquaculture: water pollution. Waste from fish farms and contaminants can directly harm fish and other aquatic organisms. It can cause deformities like gill damage, fin and tail rot, reproductive problems, and even death. Habitat degradation. This can reduce the fish population and decrease the fish size, which is harmful to the fishing industry and also impacts the economy in a negative way. Biodiversity loss. Habitat destruction and fragmentation due to fishery and aquaculture practices. Farmed fish compete, interbreed with native species, potentially leading to genetic dilution and biodiversity loss. Spread of disease and parasites. Intensive aquaculture systems can breed disease if not well managed. Disease outbreaks can spread through all aquatic life. Overfishing for fish feed. Aquaculture systems rely on fish meal and fish oil, which are sourced from wild fish. Pressure on wild fish stocks, disrupting marine food webs. Chemical pollution. To control diseases and parasites, some aquaculture operations use antibiotics and chemicals that can leach into the surrounding environment. This can result in algal blooms by overstimulating algal growth, harm local wildlife. Sixth, antibiotic resistance. All aquatic life. Mitigation strategies for sustainable aquaculture: waste management and filtration. Biological filtration systems are effective in treating dissolved waste in aquaculture, can help prevent nutrient overload in surrounding water bodies. Integrated multi-trophic aquaculture, IMTA, aim to minimize energy losses and environmental degradation by producing aquaculture species of various trophic levels together, using a circular economy strategy. Use of sustainable feed alternatives. By reducing reliance on fish meal and fish oil, these include plant proteins and oils from plants, yeast, insects, and algae. Closed containment systems. Restrict and control interactions between farmed fish and the external aquatic environment. Reducing the risk of escapees and disease transmission. Regular health monitoring and vaccination. Prevent the spread of disease in aquaculture system. Reduce the need for antibiotics and other chemicals in aquaculture. Habitat restoration and preservation. Help restore ocean health, as well as support economic development and food production. In conclusion, precision aquaculture holds immense promise for revolutionizing the aquaculture industry by integrating advanced sensors, automation, and data analytics, allowing farmers to monitor water quality. Precision aquaculture ensures better resource management, improved fish health, and higher product quality by enabling real-time data. It holds an important role in the SDG goals relating to life below water, SDG 14, and also support innovation, industry, and infrastructure, SDG 9. By embracing these innovations, it will revolutionize aquaculture and contribute to a sustainable food system for future generations. List of references. Thank you for your attention.